let's assume we can rewrite a function u of r as f of r minus f of r plus 1. Don't worry too much at the moment about how we get things into this form. We'll deal with that later. Let's just look right now at how useful it could be. So if that's the case, then r equals 1 to n of u r equals, well, it's just the sum of that function, isn't it? F of r minus f of r plus 1. So let's write out the terms for some of these values. R equals 1, or u1 equals f of 1 minus f of 2. R equals 2, u2 equals f of 2 minus f of 3, so on. And we could keep going quite some time, but we'd get a little bit bored. And so eventually we'll put some dots in here and we'll write down r of n minus 1 when r equals n minus 1, apologies. So u of n minus 1 equals f of n minus 1 minus f of n, and when r equals n, u of n equals f of n minus f of n plus 1. So now, we wanted the sum of that series. Here, listed down here, u1, u2, u3, so on, all the way up to n, un minus 1 un, that is the series. So if we added all those together, we'd get the answer to the series. But similarly, because each of these is the same, we can add up all of this. But if we look carefully here, we can see we've got f of 2 and minus f of 2. So we can cancel those two out. We've got an f of 3 and a minus f of 3. We can cancel those two out. We've got a minus f of 4 here, and we would have an f of 4 there. We've got an f of n minus 1, and we would have had an f of n minus 1 there. We've got an f of n, and we've got a minus f of n there, which leaves us just with two parts to this entire sequence. We get f of 1, and we've got a minus f of n plus 1. And so the sum of r equals 1 to n, is simply that. As you can see, that simplifies what could be a quite difficult series summation into something quite simple. So now what we have to look to do is to see, how do we get sequences in that format? So now we're going to look at example 1. We're not going to do part A because that's quite trivial. It's just a matter of rearranging that formula to get the required result. Instead, what we're going to do is we're going to concentrate on part B, where we look at finding the series summation for r cubed. So in part A, you can see we've got r cubed on one side, and we've got an expression on the right hand side. We'll leave that 4 alone at the moment. We won't worry about that for the moment. So we'll start with the summation of this expression. And if you look at this, you'll see that the left hand part of this expression is very similar to the right hand part of the expression, but with r minus 1 replacing r. So we can use the method of differences on this. So if we start out now with looking at what happens when r equals 1, we can get a value out for that expression. We can then do the same for r equals 2 and r equals 3 and so on. So let's just do that. very quickly you'll see the pattern start to appear. And once the pattern starts to appear, it becomes a lot easier to work out what the next values in this sequence are. I'm going to leave a gap and then move on to the end of the sequence, and at the end of the sequence, of course, we will get to the point where we can write down r equals n, and when r equals n, we simply have the expression above written out with n instead of r. So now we can see that we can start to cancel some of these terms. If we were to add them all up, for example, we would have 1 squared times 2 squared, and then on the second row we've got minus 1 squared times 2 squared. Similarly, we've got 2 squared times 3 squared, 3 squared times 4 squared, and so on through. And as you can see, we're cancelling diagonally from the left hand down to the right hand side. So we're left with two expressions in this list. We're left with this one, which we can cancel out because it's 0 squared, which is 0. So we're left with simply that the sum of that expression is n squared to n plus 1 all squared. Now, that is 4 lots of r cubed, and we want just r cubed. So we can finally write down that the summation of r cubed is equal to 1/4 of this expression that we've ended up with. So sigma r equals 1 to n of r cubed is 1/4 n squared n plus 1 squared. And that's it. Okay, now we're going to look at example 4. First of all, we've got to express that expression in partial fractions. That simply means to split it into two separate fractions. Let's see how we do this. Let's write down the original expression. And that is going to be equal to two separate fractions. A value we don't know over r plus 1 plus a value we don't know over r plus 3. That's just separating out the two brackets on the bottom of the original equation. And so now if we cross multiply and add together the new expression, we get the following. And now we can replace and get rid of the denominator of this expression and end up with a simple one. 2 is equal to a r plus 3 plus b r plus 1. Now substitute in two values. First of all, we substitute in a value for r equals minus 3 to get rid of the first part of the right hand side. So we end up here with 2 is equal to b into r plus 1. R plus 1 would be minus 2, so 2 equals minus 2b, so b equals minus 1. Similarly, we're going to then let r equal minus 1 to get rid of the b. So we're left with 2 equals 2a, and that gives us obviously that a is equal to 1. So our expression finally overall is 1/r plus 1 minus 1/r plus 3. So we now want to show that our original expression, 2 over r plus 1 into r plus 3, which we now know is equal to 1 over r plus 1 minus 1 over r plus 3, we want to prove that the sum of that series is in the form n into an plus b all over 6 into n plus 2 times n plus 3. So we're going to do this by using the partial fractions that we worked out before, because we know that 2 over r plus 1, r plus 3 is equal to 1 over r plus 1 minus 1 over r plus 3. So we can use that in our sum instead. So at this point we can actually start using our values of r. So let's replace r equals 1. So we get 1 over 2 minus 1 over 4. R equals 2. We get 1 over 3 minus 1 over 5. And so on and so on. We're going to go down, list these out. And if you start looking for the pattern, you'll see a slight difference to the one that went before. Previously we were able to match up terms that were just one line adrift. Now if you look carefully you can see that we'll be matching up terms that are 2 lines adrift. And also they're going to leave us with a constant in there as well. So let's finish this off. R equals n, we get 1 over n plus 1 minus 1 over n plus 3. And then we can start cancelling some of these terms out and see what we're going to be left with. And you can see if we go down there on the left hand side, we've got 1/4, but we've got minus 1/4, 1/5, minus 1/5, and so on. So you can see we're cancelling from the left hand side, but going upwards and back to do the cancellation. So that leaves us with a half plus a third minus 1 over n plus 2 minus 1 over n plus 3. And all we've got to do now is to rearrange this. So we're going to get 5/6 minus 1 over n plus 2 minus 1 over n plus 3. And bring them all together as one fraction. So we get on the top 5n plus 1 n plus 3 minus 6 n plus 3 minus n plus 2 all over 6n plus 2 n plus 3. Rearrange that to give us, end up with 5n squared plus 13n all over 6n plus 2 n plus 3. And if we rearrange that, we can see that, put those together and equate the coefficients with the original expression on the top here, we can see we get a equals 5 and b equals 13, which is what we were looking for.